Okay, thank you and good afternoon. It's great to be here. So, so this is a joint work with Alexei Gotsman from India and our respective PhD students, Sadek Kshabazi, who is in the audience, and Alejandro Nasser Pastoriza, who recently graduated from India. Okay. So, what is fault-tolerant register protocol? So, following kind of contemporary exposition of such protocols, we assume that so first we have asynchronous message passing system, and we separate between servers or replicas and clients. So we have a set of fault-prone replicas that hold the state of the register that we want to implement, that protocol implements. And we have fail-prone clients who interact with these servers using normally some kind of a quorum-based protocol, because servers can be failure-prone, to implement the register abstraction. And normally we want this register to be linearizable, even though in the literature the other conditions have been considered as well. So register abstractions are important. So why they're important is because they kind of model the basic functionality that you would expect from a distributed system, how to store the value. And over the years, register served as a sort of a benchmark problem. So people often prove floor bounds for registers because ultimately they want to learn something about consensus, but registers are much weaker abstraction. And on the other hand, you also want to implement register, right? To see if you can have some sort of a distributed storage with well-defined guarantees. And it all started from this seminal paper, and by Hagit, Barnoy, and Dolev, that was published in JCM 1995. Actually, I looked up the conference version of that was published in POTC in 1990. Okay, so this means that, so when I was preparing the slides, I was thinking, okay, so this year we're celebrating 30 years of ABD, but actually 35 years of ABD. Okay, so it's all started from here, and then it just went wild. Okay, so this is all different types of registers that people cared about. So not all of them are direct descendants of ABD, but all of them share the same flavor, that we have timestamps, we have clients, we have replicas of the values, and we use quorums. Okay. So I did some rough estimate, and I think it's probably in excess of 1,000 papers that have been published. So the last paper is, to the best of my knowledge, is in this disk, and that's our paper, and I hope you will attend the talk tomorrow. Okay, so what I'm going to talk about today is the new methodology that we came up with for proving linearizability of multi-writer, multi-reader register implementations in message passing model. And so what is linearizability? So Raisa already defined linearizability for registers, lucky for me. But just a very, very quick recap. So register implementation is linearizable if and only if for every history of read-write invocations, we can linearize this history. We can permute it in a way that it preserves the real-time order of non-overlapping invocations in the original history, and it complies with the register semantics. That means that every read returns the value written by the last write in the linearization. Okay, so now let me tell you why we actually bothered, right? So why do we need a new technique? This problem is 35 years old, right? So let me tell you this story. So we have recently been working on multi-writer register implementation in a variety of settings. So there's these 3 papers that have been published. And they all kind of share the same flavor of ABD-based protocol. And we were looking for a proof technique that we can apply to these protocols with some maybe light modification depending on the details of specific protocol, but kind of something that is general, that we don't need to reinvent something every time. And quite unexpectedly, this turned out to be a stumbling block. And why this is not easy? So first off, it is well known that textbook techniques such as linearization point arguments or forward simulations towards an atomic object don't work for ABD. So intuitively, the reason is that ABD is designed for a synchronous environment, and it proceeds by accessing quorums. And therefore, in some histories, we can't know where a specific write operation linearize until future reads what determines its position in the linearization order. Okay, so this has been well known for yeah.
Do you mean that you need like a prophecy variable or backward simulation or something?
Yes. So yeah, exactly. So one approach is to use these add-ons like backward simulation or forward and backward. So it gets complicated very quickly. Yeah. Okay. So that has been known for a long time about ABD, but the result in this 21 actually established that we have no hope for ever having a multi-write register protocol that is strongly linearizable, and it is well known that strong linearizability is equivalent to forward simulation to atomic object. Okay, so that further gives us extra incentive to look how these things can be proved in more kind of principled way. Okay, so which techniques have been used in the past? So one of them is to find, so essentially instead of reasoning inductively about states, as it is the case in forward simulations and linearization point arguments, we can look at the whole history and define the partial order on the invocations and prove that it satisfies certain properties. So this is based on a famous lemma 13.16 from Nancy Lynch's textbook, Distributed Systems Algorithms. And it was used for proving multi-writer register implementation in this paper on disk 02, which is a Rambo, also well-known algorithm. So this already goes in the right direction, but it's still not easy to use. Why? Because we need to establish the partial order first. So first we need to come up with some candidate for a partial order. Then we need to prove that it satisfies certain properties. We can kind of combine these two steps together, but that's not so easy, and it's easy to lose track of what's going on. And in addition, this technique on its own, it assumes that all invocations are complete. And since clients can be faulty, that's not necessarily the case. Okay, so those are limitations of this approach. So this approach also has been tried in a setting with the forward simulation. So what we have done in a disk paper in 2005, essentially we modeled the partial order of this lemma using an abstract automaton that we called partial order machine. And then we proved ABD, multi-write ABD by forward simulation to this partial order machine. Right? And since this partial order machine is not atomic object, that forward simulation actually works. Okay. So that's an approach. So this is something that we actually tried to adapt to our purposes. But then it turns out that simulation relation is quite complex. And then in customizing it for different algorithms that we came up with turned out to be not easy. And so that prompted us to look to alternatives. And so what is our approach? So our approach is take the idea of partial order, but flip it on its head. So what I mean by that is that we first express operation dependencies in terms of 4 standard binary relations that we borrow from weak memory literature. So these relations are not required to be partial orders. They can be cyclic, so we don't know. We just pick these 4 relations. And then, so this is these 4 relations that are well known from weak memory literature. Happens before, coherence, reads from, and from read. And then we take a union of these relations. So we do this for every history, and prove that it is that this union, which we call dependency graph, is acyclic. Okay. So that's that means that we delay the proof of partial order to the second step. So we first have some relations that might be cyclic or cyclic or acyclic, but then eventually we need to prove the partial order. Okay. So that's the approach. Any questions so far?
So those relations, they're defined, they're relating which kind of events?
Yeah, I'll show you exactly what it is. The next slide. Okay. So this results in a simple and elegant, we believe, linearizability proof of multi-writer ABD protocol, which according to Alexei in PL community, this is referred to as proof Perl. That's, yeah. And I hope you to convince that that's the case. So before I kind of plunge into defining this, so first let's say a few words about related work. So the ideas that we build upon have been circulated kind of for a long time. So some of it was folklore, some of it appears in textbooks and literature shared memory. So like, for example, this paper. Then there was a literature on database systems that defined transaction isolation properties in terms of dependency graphs. And good reference for that is the PhD thesis of Atuladia. And then more recently, there was this approach called aspect-oriented linearizability proofs. But that only was developed for shared memory, not for message passing. Another paper also looked at these techniques in the context of transactional memory. So again, this is shared memory, not message passing. Okay. So let me define the dependency graph. So we first fix an execution, sigma. And for simplicity, in order to avoid some corner cases, we assume that the first event in every execution is writing of initial value. Okay, so we don't need to deal with with all the bells and whistles defining what happens with the read when there is no any write before that read. Okay, so that's in the paper. This is general, so just for the sake of the presentation. Okay, so I start from these 3 relations, and then there is the 4th one. Okay, so real-time order, or RT. So 2 operations are related in real-time order. If the first one completes before the second one is invoked, quite straightforward. So write-write relation is a total order on all writes in the history. And write-read relation, which is known in weak memory as reads from. It's very similar to it. So write and read are in the write-read relation if read returns the value written by write. And we also need uniqueness, say that we can't have 2 pairs in the relation for 2 different writes. Okay. So far so good, I hope. So now there's a fourth relation, which is a bit counterintuitive, but it is actually crucial for the proofs to work. It's called read-write, or RW, and it is in the shared memory, in the big memory literature, it's known as from-read. Okay, so the previous one was reads from, and this one is from-read. Okay, so so RW relation actually defined in terms of the reads from relation and write-write relation. So it says that read in the relation, in the read-write relation with write, if it reads from some write that precedes this write here in the total order of writes. Okay, so graphically this looks like this. So we have total order on the writes, and then if we have a read that reads from some write, then this automatically induces all these RW edges on all subsequent writes. So that means that with these two relations, write-read and read-write, we can establish a precise ordering of reads in the stream of writes. Okay, so that would be crucial for the proofs. So to kind of jump in ahead, so what happens in the proof, that we want to argue that for linearization, reads need to return the value written by the latest write. Okay, so that means that if this is the write-read edge, so reads from this write, but somehow we have edge from this write to this write, right, which would be a violation of linearizability. But then, if we have this edge, then we also have this edge, and this is a cycle, right? So this is how it works, more or less. Okay, so let me give you an example of dependency graph in action. So here's a simple history, and here we don't have. So all writes are non-overlapping, and this read overlaps that write. So what this shows, so the red edges are the real-time edges, and the blue edges are write-write edges. And because writes are not overlapping, these write-write edges need to agree with the real-time edges, because otherwise we have a cycle. Okay, so far so good. So, but now we need, now in the interesting part, we need to see what happens with the read. Okay, so here is a violation of linearizability. So this read reads from write, which is not the latest. So, but then by the write-read read-write relation, we also have this edge. Okay, and this is a cycle, so this is not linearizable. Okay. Now, okay, so to fix it, I do the read from relation like this, and then this read goes to that write at top, and then life is good, and this is linearizable. Okay. Any questions? Okay. So another scenario which is interesting is what happens here. This is why ABD has this helping protocol for reads where reads actually have to write back. Is we have two reads which are not concurrent, but they both overlap this write. And in this case, if this read reads from that write, then it is an obligation on this read to also read from that write. So what happens if that's not the case? Have something like that. Then again we have this extra edge, and then we have a cycle here. Okay. So so just a side remark is that we can actually generalize this notion for regularity. So if you don't want linearizability, only want regularity, then you can adjust real-time relations so it doesn't have edges between the reads. So if it is like this, then we don't have cycles, and then this is regular. Okay.
Right, so some things are like forced. For instance, the two blue arrows have to be that way, but the others you can choose how you orient them. For instance, when two things are in parallel, like is that what is going on here?
So, well, when I have a specific implementation, I need to find witnesses for all these relations, and then I need to, I need to talk about the concrete. So I'm going to talk about concrete implementation, about ABD, and then it will become clear. Yeah. Okay. Okay. So this is our linearizability theorem. An execution is linearizable if and only if the union, the graph induced by the union of this relation is acyclic. We also have a, we can also come up with a result for regularity. So then, in this case, we weaken the real-time order to exclude read-read pairs, and then we have the version of this theorem for regularity. Okay. Right.
So that's a new theorem, right? Yeah, that's true.
So it's a good question. So potentially, if you write a POTSI paper and claim this is the new theorem, it will be rejected. Okay. Because a lot of it is folklore. So if you dig into the database, database literature, you will find this kind of a graph-based argument there. But we still believe that this is the novelty is that we kind of applying this in a new setting that has not been done before to our knowledge. Okay, so how we can prove the if direction of the theorem? So if we have an acyclic dependency graph, so this is an acyclic dependency graph. So if we have a cyclic dependency graph, then it induces a partial order, and this is a partial order, a bit simplified of a version of the previous picture. And every partial order can be extended into a total order by axiom of choice. Okay, so here in this partial order, it's not a total order because these two reads are not ordered, so we can just extend it like this. And then
are we infinite here?
Yeah, so that's a very good question. I meant to say that yes, we proved this for infinite executions. It was actually quite tricky to do, so we had to use the axiom of choice and these kind of things.
I was asking why you need the axiom of choice for totally linearizing a partial order, but I guess an infinite execution will take some more sophistication.
Yes, exactly.
But there's also the difference between countable and uncountable. Do you, like, I can expect axiom of choice to be needed for uncountable stuff, but
probably countable suffices, probably.
Right.
Yeah. So we do this for infinite executions. It's also important because then we can have an extension of linearizability for infinite executions. Okay, and this is a linearization. Why this is a linearization? Because obviously it includes all the red edges, which is the real-time order, and every reads from the last preceding write in the total order. Okay, because of this yellow from read edges, as I explained before. Okay, so now I want to demonstrate you the proof of ABD with this theorem. Okay, so if you have any questions so far, please ask. Yeah.
So what's the high-level plan? So you're going to, as you said, materialize those relations?
Yeah, I'm going to come up with witnesses for all four relations.
And prove that it's acyclic.
And then I prove that the graph is acyclic, yeah. And it turns out that I can do this in 3 slides.
Okay.
which feels like an accomplishment. Okay, so ABD, according to contemporary expositions, works with a read-write quorum system. So we make typically this threshold assumption about the number of replicas. So we have 2f plus 1 replicas. Let's say we consider crash failures here. Okay, so read quorums can be any set of size f plus 1, write quorums any set of size n minus f. And any two sets like that are guaranteed to intersect. So we have this consistency property, and also we require availability property for liveness. So we have a available read and write quorum in every execution. Okay. So then this is the ABD protocol, multi-writer ABD protocol. So write starts by reading a quorum, gets a set of timestamps, and then select and timestamp is a pair of counter and the identifier of the writer. Okay, so then it selects the highest counter, increments it by 1, adds its own identifier, and writes this to the quorum. Okay, so reads a quorum to get pairs of timestamp values, then selects the timestamp value with the highest timestamp, and then writes it back. Okay. So this is the write back mechanism of ABD, or helping mechanism that is needed for linearizability of non-overlapping reads. Okay, so these functions that I use here, write quorum and read quorum, are straightforward. Just send a request to all processes, to all replicas, and wait for a quorum of responses. So it's a write quorum for write request and read quorum for read request. Any questions? So the protocols on replicas also are quite simple. So on the write, I get a pair of timestamp value. If this timestamp is higher than the timestamp and value that I'm storing, I reassign it to what I got. And in any case, I send back an acknowledgement. And for read, I simply return either timestamp or I return this pair timestamp value. Okay. So any questions so far? No? Everyone is familiar with ABD, right? Okay, so now how we prove it. So first we define a function, TS, so that's, I'm going to use it in the next slide. And so this function would map every operation, every invocation in a history to a timestamp. Okay, so how I select this timestamp? So for writes, this is the timestamp. This is how I select the timestamp for a write. So this is the timestamp assigned in this line. And so this is the timestamp with which I would write a new value. And for read, this is the timestamp which is associated with the value that I'm going to return. Okay. All right. Okay, so now let's construct the relations. So write relation is equivalent to this condition of timestamp of one of the writes to be strictly less than the other one, and this simply follows from timestamp uniqueness. So it's straightforward. So for a reads from relation. So the write and read are in read from in this WR relation if they have the same timestamp. Okay. So that's exactly as what happens in the ABD logic. The read returns a value with the timestamp of some write. Right? That's hope this is intuitive. Okay. So read-write is just obtained from these two relations that I have shown before, and it implies that if we have read-write in this RW relation, then timestamp of this read is strictly less than timestamp of this write. Okay. The proof is here. And finally, by quorum intersection and update rule and the write-back mechanism together, we also have this result that for any operation read or write which leads to write in real-time order, we have a strict inequality here. And if it leads to read, then we have a non-strict inequality, right? So in particular, if we have two reads that are in a real-time order, then they can have the same timestamp. Yeah. Okay. Well, any questions about it? Okay. Right. Okay. So now, I promised the proof in 3 slides. So this is the first slide. Okay. So let's take an execution sigma of multi-writer ABD. Construct a dependency graph as above, but using these witnesses that we have found. Now, suppose by contradiction that this graph has a cycle, then my first lemma is this cycle can only include read operations. Okay, so why is that? So suppose that it includes write operation. Right? So if it includes write operation, then we know that this x must have a timestamp greater or equal than the timestamp of this write, because this is how we constructed our relations. Okay. Then we have 3 cases based on what is on this edge here. Okay. Right. So it's either a WW edge, it's RW, or a real-time edge. Okay. We have only 3 cases here that edge can go into a write. However, for all these 3 cases, we have a strict inequality here. Right? So the timestamp of write is strictly greater than the timestamp of x. If you combine these 2 inequalities, we get that timestamp of x is greater than timestamp of x, of course, the contradiction. Okay. So we proved that this cycle only includes reads. And then, since it only includes reads, all the edges here must be real-time edges, because that's the only edges that are possible between reads, okay, by definition. But that would mean that some read has started before it has finished, and that's, of course, the contradiction. That completes the proof of linearizability of multi-writer ABD. Okay. So any questions? So my next slide is conclusions, I believe. Okay. All right, so I showed you what we consider, and hope I convinced you to some extent, the proof pearl of linearizability for message passing implementation of multi-writer, multi-reader register. So if you have been listening carefully, you might have noticed that I cheated a little bit because I assumed that all operations are complete. But in the paper, we have an easy generalization for incomplete operations that uses visibility predicate. And that was first introduced in this paper. And that was, we also used this in this paper as well. So it does work. So there is an easy extension to support incomplete operations. So as has been noticed that we proved the linearizability theorem for infinite executions. And this is interesting because in the literature, there are generalization of linearizability that preserve liveness properties. And for that case, we do want to have linearizability on infinite executions. Okay, so it's an add-on bonus. And the last thing I wanna, it's more like something to discuss with the automated verification community, is how we can actually automate proofs like that, right? Because I'm not an expert, but as far as I know, you guys use this invariant reasoning and essentially similar to forward simulation. And here, I need somehow reason about whole traces, so I need ways to encode traces. So, and like I can imagine an array in memory, and then I index it in this array, etc., etc. So I don't know how that can be done, if it can be done, but I just put out this question. And that's complete.
Thank you very much. Yes.
You said you want to reason on infinite executions. Have you tried co-inductive methods?
Which method?
Co-inductive methods?
I don't get the terminology.
Co-inductive.
Co-inductive, no. I don't know what it is. Yeah, I will look it up. Thanks.
So what would you consider was the real meat or the real key ingredient in the proof? Was it the abstract level where you proved that if there's no cycle, then
the actual if you compare that to the partial order proofs that I mentioned initially, they kind of these two approaches they're very much related. But the problem with partial order is that I need first to materialize this partial order, and then I need to prove some property that depends on something already being a partial order. But what if this is not a right partial order? So I need to kind of repeat this cycle. So here, it's much more constructive, I would say. It's this constructiveness. This is what is attractive in this proof. That I first just have to specify these four relations, and I don't care if they're partial order. They can be any. They just extract something directly from the timestamp, right? And then comes the part where I have to show a cyclicity, right? So I would say that the constructiveness of this approach is what is most appealing.
But before that, so once you define the relation, you still have to prove that there is some kind of well-formedness condition or something, because I could come up with random relations that would be nonsense, right?
No, I need to give this relation that complies with the properties of these abstract relations, right? So
yes.
Relations that witnesses that I pick, they.
So you know, the way, I think it's in our book, Jennifer, and it's definitely the way I teach it in class.
Oh, you have this proof in the book?
Not this proof, but the proof for multi-right. I think it's in the book. It's definitely something I teach in my course. And the way we do it is we totally order the writes by their timestamps, and then we insert the reads in appropriate places. And the way we do it is we insert them after the write they read from, but not after. We insert them right before the next write.
Yes, this is what we're doing.
So that's essentially what will happen here.
Yep.
So it's a constructive proof in a way, but it relies on first doing all the writes.
Yes.
And then finding the right place for the reads, and then showing that we are not reordering or misordering reads, based on something pretty similar to a property that you have here, because of core intersection for the right back.
Yep.
Actually, there's at least one student from my class.
Yeah, so we used actually this same technique for three different protocols in it.
So, and also there's like a corner case of what to do if there's no last. Actually, there is the last write. So where do you put all the following reads? And
If there is
like an imaginary last write.
Yeah, this is what I did in the talk, but in the paper we have we handle
So
this
we actually have
problem.
a problem with the last write, not with the first write. But
The last one.
yeah, if there's a last write, where do you put all the final reads? You need to put them before the next write. But if there's a finite number of writes, there's no next write to put before.
Yeah,
So
then they just read from like last write. It's,
no, but the idea is you don't put after the write you read from. You put before the write after that. So this places the reads, because we consider the reads in the order they appear in the execution, they complete or start in the execution, and this gives you the time ordering. It's actually a neat proof. But I don't know how it would generalize for more sophisticated algorithms, definitely. I want to say something else, by the way. Original IAPD, actually, a lot of the effort went into not using infinite timestamps. And that's a whole different ballgame to do the linearization when there's not an obvious total order on the right.
It's a good point, yeah. If we can use the kind of similar technique, if the timestamps are finite, yeah. Yeah, good point.
And today nobody cares about finiteness, but
yes,
it was a
yeah.
big deal.
Back in the day, yeah.
So that would make the algorithm more complex, but the technique could still apply, right?
If the timestamps are bounded?
Yeah.
That's a good question. That's
You don't
I've never thought about it. Yeah, because here it was very easy to come up with these witnesses.
Right.
You just yeah, because time steps are infinite. So yeah, but if they're not, if there is a reuse of timestamp, then it needs to be more sophisticated, I suppose.
And did you try to find the prophecy variable version of the proof by any chance, or?
No, we gave up on these approaches before we cooked up this theorem, and then we just saw that this works really well, and then we decided why bother.
Sure. All right. Any other questions before we go to break? All right. Well, thanks again.
Thank you.